Our ancestors thought that the earth was stationary and all the other celestial bodies rotated around it. Today, it is well established that the earth rotates around the sun. Rotating objects seem to rotate around an axis. How does that work? For example, take this basketball and spin it. Can you identify its axis? Imagine a line around which all the points on the ball are rotating. This line would be its axis. Now I can change this axis. It could be here or something along this line. Thus, we can say that the axis is an imaginary line around which a body rotates. Just like this ball, the earth also has an axis around which it rotates. This imaginary line passes through the north and the south poles of the earth. We know the earth rotates on its axis from west to east. That's why we observe sunrise in the east and sunset in the west. Now, what is the speed of Earth's rotation? Let's calculate it. The radius of the Earth at the equator is 6,378 kilometers. Thus, the circumference of the Earth will be 2 pi into radius. That is roughly around 40,075 kilometers. This means to complete one full rotation from a given point on the equator, one will have to travel this much distance. So what will be the speed of that point? That will be 40,075 kilometers divided by 23.93 hours, and that gives us 1674.4 kilometers per hour. But there's a catch here. Not all points on the earth have a velocity of 1674.4 kilometers per hour. As we move towards the poles, the distance of a point on the surface of the earth from the axis of earth decreases. This decreases the distance that a point needs to travel in one rotation. And this in turn reduces its velocity. Suppose this point is at a distance of 3,000 kilometers from the axis. Therefore, the circumference of this point will be 2 pi into radius, that is approximately 18,850 kilometers. So the velocity at this point shall be 18,850 kilometers divided by 23.93 hours, which comes out to be 787.71 kilometer per hour. So we observe a clear reduction from 1674.4 kilometer per hour to around 700 kilometer per hour. Thus, we can say as we move from the equator towards the poles, the velocity reduces. When the Earth rotates on its axis, it has certain effects. One of the most important effects of the rotation of the Earth is the occurrence of day and night. Let's assume this source of light is the sun and this is our Earth. When I switch on the light shines on the Earth. As you can see, this part of the globe is in sunlight. Hence, it experiences daytime, while this dark part experiences nighttime. But this arrangement changes as the Earth rotates. The day changes into the night and vice versa, right? Now, if I were to take a marker and make a circle where I can see the approximate boundary between the light part, which is the day, and the dark part, which is the night, I will in fact get a circle all around the planet. This is called the circle of illumination. Thus, we can say the circle of illumination is the division between day and night. Now, the rotation of Earth also causes the Coriolis effect. The Coriolis effect explains how the wind direction is affected by the Earth's rotation. Due to the rotation of the Earth, the winds get deflected to the right in the northern hemisphere and to the left in the southern hemisphere. But how does the rotation of the Earth deflect the winds? Let's understand this with the help of an example. Let's suppose we have three cars, A, B, and A dash. All the three cars are moving with the same speed. Suppose you are traveling in car B while two of your friends are in car A and A dash. Suppose your friend in car A throws a ball towards you. What will happen? Would you be able to catch it? Yes. Even though you are in a moving car, still you would be able to catch the ball. This is because both of you and your friend are moving with the same speed. Now, let's give a small twist to the situation. Let's assume A and A dash have equal speed, while B's speed is more than both the cars. And all three of them are moving from west to east. Now, we will perform a small activity in 4 different scenarios. In the first case, we'll focus on car A and B. We know that car B is traveling faster than A. If you throw a ball from B to your friend in car A in a straight line, then what will happen? Would he be able to catch it? Well, no. The ball will appear to land to the right of your friend because he is moving slower and has not caught up. Now consider the second case. Here, ball is thrown by your friend from car A to you in car B. When your friend throws the ball to you, it will again appear to land to the right of you. But this time, it's because you are moving faster than your friend and you have moved ahead of the ball. Now, in case 3, let's focus on car B and A dash. If a ball is thrown by you in car B to your friend in car A dash, the ball will appear to land to the left of your friend because he is moving slower and has not caught up. And in the fourth case, if the ball is thrown by your friend in car A dash to you in car B, then it will again appear to land to the left of you. But this time, it's because you are moving faster than your friend and you have moved ahead of the ball. Now, something similar happens with Earth as well. Car B can be imagined as a point situated on the equator, and car A and A dash can be imagined as the points in the northern and the southern hemispheres respectively. The point on equator is traveling faster than a point in the northern and the southern hemisphere. Thus, if a ball is thrown in a straight line from equator to the northern hemisphere, it will appear to take a curved path towards right, and if it is thrown from a point in the northern hemisphere towards equator, still it will appear to have taken a curved path towards its right. Situation gets reversed when we consider the southern hemisphere. A ball thrown from the equator towards the southern hemisphere will appear to have taken a curved path towards its left. And if the ball is thrown from a point in the southern hemisphere towards the equator, still it will appear to have taken a path curved towards the left. In this entire exercise, always remember, left and right deflections are decided on the basis of the direction of propagation of the ball. This apparent deflection is the Coriolis effect. Fluids traveling across large areas, such as air currents, are like the path of the ball. They appear to bend to the right in the northern hemisphere. The Coriolis effect behaves the opposite way in the southern hemisphere, where currents appear to bend to the left. There are certain factors on which the degree of deflection caused by the Coriolis force depends. First is the velocity of the moving object. The degree of deflection is directly proportional to the velocity of the moving object, meaning higher the velocity of the moving object, higher will be the deflection. Secondly, it depends on the latitude. Coriolis force is maximum at the poles and is almost absent at the equator. And why is it like this? Well, let's understand. In the equatorial region, that is from around 5 degrees north to 5 degrees south, the speed of Earth's rotation will be almost similar, meaning all the points will be traveling nearly at the similar speed. So if you throw a ball from equator to the 5 degrees north latitude, the deflection will be almost negligible. And more you get closer to the equator, the deflection will get smaller and smaller, and finally at the equator, it will be completely zero. Now let's see what happens in the polar regions. We know that Earth is not a perfect sphere. Rather, it is slightly bulged at the equator and flattened at the poles. Because of this flatness, poles experience maximum Coriolis force. Let's imagine the North Polar region to be as flat as a merry-go-round. Now mark 4 points on this merry-go-round: A, B, C, and D. Now, because Earth is rotating from west to east, then from our perspective, the merry-go-round will be rotating in a counterclockwise direction. If A throws a ball towards C, what do you think? Would C be able to catch it? Well, no. Because by the time the ball will traverse its path, the position of C would have been replaced by B. Thus, from the perspective of A, it will appear that the ball has deflected almost by 90 degrees towards the right. Something similar happens in the polar regions as well. Because of their flatness, a deflection of nearly 90 degrees can be observed, and thus Coriolis force is said to be maximum at the poles and minimum at equator.